Chapter 9. Filling the Gaps. For is and is not, though with rule and line, and up and down by logic I define, of all that one should care to fathom I was never deep in anything but wine. Ah, but my computations, people say, reduced the year to better reckoning? Nay, 'twas only striking from the calendar, unborn tomorrow and dead yesterday. Omar Khayyam. The admission of the validity of infinite process takes us out of the narrow confines of the rational domain and furnishes us with a means of attacking problems before which rational arithmetic stood powerless. It is therefore natural to inquire whether we are now in a better position to solve the old problem of establishing a perfect correspondence between the points on a line and the domain of numbers. We know that rational arithmetic was incapable of solving this problem, but whether general arithmetic, the arithmetic of real numbers, fares better in this respect is still an open question. The points of the line which eluded rational representation, are they at all capable of arithmetical formulation? The old problem which caused the original crisis and forced a revision of the foundations of arithmetic now reappears in a new and more general form. Can any real number be represented by a point on a line? Can a real number be assigned to any point on a line? If the answer is in the affirmative, then there exists a complete and reciprocal correspondence between the domain of real numbers on the one hand and the aggregate of points on the other. If such a correspondence exists, we can confidently use the intuitive language of geometry in the formulation of arithmetical analysis, and reduce these questions to number and magnitude. We see how fundamental the query is, and how much may depend on the answer. To understand the answer that has been given to this question in modern times, we must give ourselves separate accounts of the nature of the two aggregates, the domain of real numbers and the points on a line. Of the real domain we know, first, that it is well ordered. Of any two real numbers a and b, we can tell which is greater. Furthermore, if a is greater than b, and b is greater than c, then also a is greater than c. In short, we can by an act of the mind arrange any infinite collection of such numbers in their order of magnitude, and we can further conceive that all real numbers have been so arranged. This is what we mean by saying that the aggregate of real numbers is well ordered. Second, that this domain has neither a first nor a last member. No matter how great a positive real number is, there is one greater, and no matter how small a negative number is, there is one still smaller. We express this by saying that the real domain extends from negative infinity to positive infinity. Third, that among the real numbers all rational numbers are to be found. The rational domain is but a subdomain in the greater real domain. Fourth, that the aggregate of real numbers is everywhere dense. Between any two real numbers, no matter how small the interval, an infinite number of other real numbers may be inserted. Does it not follow from this that the domain of real numbers is all-embracing? Well, we should be tempted to affirm this without hesitation, if it were not for our experience with the rational numbers, for let us remember that so far all we have said of the real domain could apply equally well to the rational. Yet in spite of the compact structure of the latter we found it full of gaps. What assurance have we, indeed, that the irrationals and the transcendentals have completely filled these gaps, that on some perhaps not so very far distant day new processes will not be discovered, which by creating new mathematical beings will expose new gaps, this time in the real domain? To answer this question, Cantor undertook to probe the fundamental difference between the rational and the real domains. The aggregate of rational numbers, while well ordered and compact, is imperfect. It is imperfect because it is not closed with respect to infinite processes. It is not closed to infinite processes, as the very existence of irrationals shows, because there exist infinite rational sequences which, while convergent, have no rational numbers for limits. In short, the aggregate of rational numbers is imperfect, because it does not contain all of its own limiting values. But the aggregate of real numbers is not only well ordered and compact, it is perfect. It is perfect because it is closed to all infinite processes. An infinite sequence of real numbers, if convergent, represents a real number. Indeed, such an infinite sequence, if not rational itself, could be replaced by a rational sequence which would converge to the same limit, and this limit is by definition a real number. The aggregate of real numbers contains all its own limiting values, and for this reason is perfect. Now, not every compact aggregate is perfect, as the analysis of the rational domain shows, but every perfect aggregate is compact, as Cantor proved. An aggregate which is both well-ordered and perfect Cantor defined as a continuum. The real number domain constitutes a continuum, the arithmetic continuum. The domain of rational numbers, on the other hand, being imperfect, does not constitute a continuum. And so what describes the domain of real numbers exhaustively is that it is a continuum in the Cantor sense. Now, as we saw, the words continuum, continuous, continuity were used in the exact sciences from their very beginning. From time immemorial, the term continuous has been applied to space, time, and motion in the undetermined sense of something uninterrupted, something that is of the same nature in its smallest parts as it is in its entirety, something singly connected, in short, something continuous. Don't you know? It is one of those vague, loosely conceived notions of which intuition perceives the sense, and yet any attempt to formulate it in a precise definition invariably ends in an impatient, "Well, you know what I mean." The prototype of all ideas which meet these specifications is the line, and particularly the straight line, which in our mind is endowed with this continuity par excellence. So that if we are to have a complete and reciprocal correspondence between the line and the real domain, we must make sure that there is no flagrant contradiction between this intuitive idea of continuity we ascribe to the line and the precise, scientifically formulated continuity of real numbers as defined by Cantor. If, without venturing on a precise formulation of our intuitive idea of continuity, I should try to describe roughly what I mean by continuous, I should be thinking aloud as follows, quote, "Time is the essence of all things. Mother Nature makes no jumps, because Father Time knows no jumps. Time cannot be conceivably interrupted. That is why there is nothing spontaneous in nature. Time flows on, and in its flow it carries all things conceivable." End quote. And so when we attempt to describe the continuity of any phenomenon, we find ourselves invariably, even if unconsciously, invoking the continuity of time. The line appears to us as the prototype of all things continuous, because we conceive it as generated by a continuous passage, because to our minds it is but a concrete representation of the stream of time, frozen as it were. So too is it with other phenomena. The mind shrinks before the spontaneous. That is why our scientific theories cling so desperately to evolution. Be it a cosmogony, a theory of life, or a sociological hypothesis, everywhere we find this horror of the cataclysm. At any cost, we refuse to recognize that catastrophe and revolution, spontaneous generation and accidental discovery, may have been dominant factors in the history of the universe or of the race. And just as evolution gives us a smooth picture of our past, the doctrine of causality, by linking all phenomena into one continuous chain, safeguards our future against all spontaneous disturbances and protects us against the horror of chaos. These vague ideas of continuity and causality are so closely associated that one is constantly invoked to support the other. And no wonder, our belief in the continuity of the universe and our faith in the causal connection between its events are but two aspects of this primitive intuition that we call time. And so on the one hand there is the conviction that natura non feci saltus, and on the other hand arises the illusion, post hoc, ergo propter hoc. Herein I see the genesis of the conflict between geometrical intuition, from which our physical concepts derive, and the logic of arithmetic. The harmony of the universe knows only one musical form, the legato, while the symphony of number knows only its opposite, the staccato. All attempts to reconcile this discrepancy are based on the hope that an accelerated staccato may appear to our senses as a legato. Yet our intellect will always brand such attempts as deceptions and reject such theories as an insult, as a metaphysics that purports to explain away a concept by resolving it into its opposite. But these protests are in vain. To bridge the chasm between the continuity of our concept of time and the inherent discontinuity of the number structure, man had to invoke once more that power of his mind which knows itself capable of conceiving the indefinite repetition of the same act when once this act is impossible. This was the historic role of the infinite. This is why, through the ages, the problems of the continuum and of the infinite were but the two horns of a single dilemma. This long process of adaptation has now culminated in the Cantor theory, in which any number is conceived as the goal of an infinite succession of jumps, and the continuum is regarded as comprising not only all possible resting stations, but all possible goals as well. It is a staccato theory par excellence, and yet it does not escape the tyranny of time. It merely adapts itself to this tyranny by complacently regarding the flowing stream of duration as an infinite succession of pulsations of furiously accelerated tempo. The mind rebels against this tyranny. The mind demands a theory of number free from the extraneous influences of geometry or mechanics. So history was to witness one more gesture. This took the form of a new theory of irrationals which bears the name of its author, Richard Dedekind. The essence of the Dedekind concept is contained in the following passage taken from his epoch-making essay, Continuity and Irrational Numbers, which appeared in 1872, 10 years before the Cantor essays on the same subject were published. Quote, "The straight line is infinitely richer in point individuals than the domain of rational numbers is in number individuals. If then we attempt to follow up arithmetically the phenomena which govern the straight line, we find the domain of rational numbers inadequate. It becomes absolutely necessary to improve this instrument by the creation of new numbers, if the number domain is to possess the same completeness, or as we may as well say now, the same continuity as the straight line. The comparison of the domain of rational numbers with a straight line has led to the recognition of the existence of gaps, of a certain incompleteness or discontinuity in the former, while we ascribe to the straight line completeness, absence of gaps, or continuity. Wherein then does this continuity consist? Everything must depend on the answer to this question, and only through it shall we obtain a scientific basis for the investigation of all continuous domains. By vague remarks upon the unbroken connection in the smallest part, nothing obviously is gained. The problem is to indicate a precise characteristic of continuity that can serve as a basis for valid deduction. For a long time I pondered over this in vain, but finally I found what I was seeking. This discovery will perhaps be differently estimated by different people. The majority may find its substance very commonplace. It consists in the following. In the preceding section, attention was called to the fact that every point of the straight line produces a separation of it into two portions, such that every point of one portion lies to the left of every point of the other. I find the essence of continuity in the converse, i.e., in the following principle. If all points of a straight line fall into two classes, so that every point of the first class lies to the left of every point of the second class, then there exists one and only one point which produces this division of all points into two classes, this severing of the straight line into two portions. As already said, I think I shall not err in assuming that every one will at once grant the truth of this statement. Moreover, the majority of my readers will be very much disappointed to learn that by this commonplace remark the secret of continuity is to be revealed. To this I may say that I am glad that everyone finds the above principle so obvious and so in harmony with its own ideas of a line, for I am utterly unable to adduce any proof of its correctness, nor has anyone else the power. The assumption of this property of the line is nothing else than an axiom by which we attribute to the line its continuity, by which we define its continuity. Granted that space has a real existence, it is not necessary that it be continuous. Many of its properties would remain the same if it was discontinuous. And if we knew for certain that space was discontinuous, there would be nothing to prevent us, in case we so desired, from filling up its gaps in thought, and thus making it continuous. This filling up would consist in the creating of new point individuals, and this would have to be effected in accordance with the above principle." End quote. Let us analyze the Dedekind principle at work. Like Cantor, Dedekind takes for his point of departure the domain of rational numbers. However, instead of identifying the real number with a convergent sequence of rationals, he views the real number as generated by the power of the mind to classify rational numbers. This special classifying scheme he calls Schnitt, a term which has been variously translated as the Dedekind cut, split, section, and partition. I choose the last. This partition is the exact counterpart of the concept which Dedekind used in defining the continuity of a line. Just as any point on the line severs the line into two contiguous, non-overlapping regions, so does every real number constitute a means for dividing all rational numbers into two classes which have no element in common, but which together exhaust the whole domain of rational numbers. Conversely, any equation, any scheme of classification, any process which is capable of effecting such a split in the domain of rational numbers is ipso facto identified with a number. It is by definition a real number, an element of the new domain. The rational numbers are a part of this vast domain because each one individually can be regarded as such a classifying scheme. Indeed, with respect to any given rational number, say 2, all rational numbers can be divided into two classes. Those that are less than 2 or equal to it go into the lower class. Those that are greater than 2 into the upper class. The two classes have no elements in common, and together they exhaust the whole aggregate of rational numbers. The rational number 2 may be regarded as a partition and is therefore a real number. But obviously the potentialities of this far-reaching principle cannot be exhausted by such trivial partitions. Nothing, for instance, can prevent us from partitioning all rational numbers into those whose square is less than or equal to a given rational number, say 2, and those whose square is greater than 2. These two classes are mutually exclusive, as was the case in the previous example, and as before, the two classes taken together exhaust all rationals. This partition, too, defines a real number which we identify with our old friend, root 2. On the other hand, while both rational and irrational numbers may be represented by partitions, the choice of rationals for basis is not without consequence. For there is an essential difference between rational and irrational partitions. The rational partition is itself a part of the lower class. It is as if a politician had split a party and joined the left wing. But the irrational partition is completely ex parte. It is as if an issue had split the party, the issue being a part neither of the left nor of the right wing. And so here the irrational that caused the partition belongs neither to the lower nor yet to the upper class. In other words, in the rational case, the lower class has a greatest element and the upper no least. In the irrational case, the lower class does not have a greatest element, nor yet does the upper class have a least. According to the Dedekind theory, this is the only feature which distinguishes the two types of number. It is characteristic of a rational number to belong to one of the classes, and it is just as characteristic of the irrational to belong to neither. To prove that the Dedekind partitions are bona fide numbers, it must be shown that they satisfy all the stipulations of the principle of permanence. What I said in the preceding section proves that the first stipulation is satisfied. That this is also true of the others can be proved with utmost simplicity and perfect rigor. The criteria of rank, the definition of operations, the proof of the associative, the commutative, and the distributive properties of these operations, all are the exact counterparts of the corresponding propositions in the Cantor theory, and I shall not bore the reader with the details. The fundamental theorem in the Cantor theory, That the domain of real numbers is closed with respect to infinite processes also has its counterpart in the Dedekind theory. Having defined the domain of reals, it is natural to inquire again whether a subsequent application of the principle would not still further extend the domain. In other words, let a partition be now effected which would split all the real numbers into two classes. Could such a partition create a new type of magnitude not found among the real numbers? The answer is no. Any such partition can be brought about by a partition in the rational domain. The aggregate of all partitions of the rational domain is closed. The complete equivalence of the two theories of the arithmetic continuum has been recognized by the authors themselves, and their rivalry, if there ever was a rivalry, is today only an historical incident. To any partition in the rational domain corresponds a limiting value of an infinite sequence, and conversely a limiting value of any infinite sequence can be used as an agent for the partitioning of the rational domain. All conceivable partitions on the one hand, all the limiting values of rational sequences on the other, are identical, and are just two descriptions of the same aggregate, the arithmetic continuum. From the metaphysical standpoint, this seems very puzzling indeed. As I have said before, the Cantor theory is the consummation of a long historical process. The Dedekind partition is a bold and original conception. The Cantor theory uses the infinite process to generate the number domain, whereas nowhere in the definition of the real number does Dedekind use the word infinite explicitly, or such words as tend, grow beyond measure, converge, limit, less than any assignable quantity, or other substitutes. Again, the Cantor theory is frankly dynamic. The limiting value is being generated in a manner which strongly resembles the motion of a point attracted to a center. The Dedekind theory is essentially static, no other principle being utilized than this power of the mind to classify elements along a definite scheme. So it seems at a first glance that here we have finally achieved a complete emancipation of the number concept from the yoke of the time intuition which long association with geometry and mechanics had imposed upon it. And yet the very equivalence of two theories so opposite in their points of departure and so different in their modes of attack shows that things are not so happy with the Dedekind principle as may first appear. And indeed a further analysis of the Dedekind procedure discloses that the infinite here is implied, even if not explicitly used. The principle of partitioning, if effected upon a finite set of rational numbers, would lead to trivialities, which would at once betray its futility. Furthermore, any practical application of the principle towards the determination of an irrational number necessitates the employment of a machinery analogous to the infinite sequence of Cantor. And the same is true of the relation of the theory to the time intuition. The axiom of Dedekind, if all points of a straight line fall into two classes, such that every point of the first class lies to the left of any point of the second class, then there exists one and only one point which produces this division of all points into two classes, this severing of the straight line into two portions. This axiom is just a skillful paraphrase of the fundamental property we attribute to time. Our intuition permits us, by an act of the mind, to sever all time into the two classes, the past and the future, which are mutually exclusive and yet together comprise all of time, eternity. The now is the partition which separates all the past from all the future. Any instant of the past was once a now, any instant of the future will be a now anon. And so any instant may itself act as such a partition. To be sure, of the past we know only disparate instants, yet, by an act of the mind, we fill out the gaps, we conceive that between any two instants, no matter how closely these may be associated in our memory, there were other instants, and we postulate the same compactness for the future. This is what we mean by the flow of time. Furthermore, paradoxical though this may seem, the present is truly irrational in the Dedekind sense of the word. For while it acts as partition, it is neither a part of the past nor a part of the future. Indeed, in an arithmetic based on pure time, if such an arithmetic was at all possible, it is the irrational which would be taken as a matter of course, while all the painstaking efforts of our logic would be directed toward establishing the existence of rational numbers. Finally, when Dedekind says that if we knew for certain that space was discontinuous, there would be nothing to prevent us, in case we so desired, from filling up its gaps in thought and thus making it continuous, he states a post factum. This filling out process was accomplished ages ago, and we shall never discover any gaps in space for the simple reason that we cannot conceive of any gaps in time. Yet in spite of the fact that neither Cantor nor Dedekind succeeded in emancipating the continuous from the intuition of time, the age-old conflict between our notions of continuity and the scientific concept of number ended in a decisive victory for the latter. This victory was brought about by the necessity of vindicating, of legitimizing, as it were, a procedure which ever since the days of Fermat and Descartes had been an indispensable tool of analysis. The history of this discipline, analytic geometry, forms a part of the next chapter. It will suffice for my purposes here to state that this discipline, which was born of the endeavors to subject problems of geometry to arithmetical analysis, ended by becoming the vehicle through which the abstract properties of number are transmitted to the mind. It furnished analysis with a rich, picturesque language and directed it into channels of generalization hitherto unthought of. Now, the tacit assumption on which analytic geometry operated was that it was possible to represent the points on a line, and therefore points in a plane and in space, by means of numbers. This assumption is of course equivalent to the assertion that a perfect correspondence can be established between the points on a line and the real numbers. The great success of analytic geometry, the fact that it is so admirable, served the purposes of both analysis and geometry, gave this assumption an irresistible pragmatic force. It was essential to include this principle in the general logical structure of mathematics. But how? Under such circumstances, mathematics proceeds by fiat. It bridges the chasm between intuition and reason by a convenient postulate. This postulate ousts the intuitive notion and substitutes for it a logically consistent concept. The very vagueness of all intuition renders such a substitution not only plausible, but highly acceptable. And so it happened here. On the one hand, there was the logically consistent concept of the real number and its aggregate, the arithmetic continuum. On the other hand, the vague notions of the point and its aggregate, the linear continuum. All that was necessary was to declare the identity of the two, or what amounted to the same things to assert that it is possible to assign to any point on a line a unique real number, and conversely any real number can be represented in a unique manner by a point on the line. This is the famous Dedekind-Cantor axiom. This proposition, by sanctifying the tacit assumption on which analytic geometry had operated for over 200 years, became the fundamental axiom of this discipline. This axiom, like so many others, is really a disguised definition. It defines a new mathematical being, the arithmetical line. Henceforth the line, and consequently the plane and space, ceases to be an intuitive notion, and is reduced to being a mere carrier of numbers. And so this axiom is tantamount to the arithmetization of geometry. It means the emancipation of analysis from geometrical intuition, to which it owed its birth and growth. It means more. It is a bold declaration that henceforth analysis proposes to assume control over geometry and mechanics, and through them to control those other phases of our cognition, which are even nearer to the crude reality of our senses. The age-long struggle to create an arithmetic in the image of that reality had failed because of the vagueness of that reality. So arithmetic created a new reality in its own image. The infinite process succeeded where the rational number had failed. Numeri mundum regnant. Chapter 10. The Domain of Number. Quote, To Archimedes came a youth eager for knowledge. Teach me, O master, he said, that art divine, which has rendered so noble a service to the lore of the heavens. And back to Uranus yet another planet revealed. Truly, the sage replied, this art is divine, as thou sayest. But divine it was ere it ever the cosmos explored. ere noble service it rendered to the lore of the heavens, and back to Uranus yet another planet revealed. What in the cosmos thou seest is but the reflection of God. The God that reigns in Olympus is number eternal. K.G.J. Jacobi. By trying and erring, by groping and stumbling, so progressed our knowledge. Hampered and yet spurred by a hard struggle for existence, a plaything of his environment and a slave to the traditions of his time, man was guided in this progress not by logic, but by intuition and the stored-up experience of his race. This applies to all things human, and I have made painstaking efforts to show that mathematics is no exception. And yet who knows but that the habit of systematic exposition acquired by years of teaching has caused me to transgress unwittingly. Now the evolution of number, when presented in broad outline, does seem to possess a certain logical continuity. But a broad outline is usually a crude outline. It teaches little of true significance. The irregularities of a curve apprise us more of its true nature than does its shape. Similarly, the irregularities in the development of any human endeavor bring out more clearly the underlying factors than do those features that it has in common with similar endeavors. The systematic exposition of a textbook in mathematics is based on logical continuity and not on historical consequence, but the standard high school course, or even the college course in mathematics, fails to mention this fact, and therefore leaves the student under the impression that the historical evolution of number proceeded in the order in which the chapters of the textbook were written. This impression is largely responsible for the widespread opinion that mathematics has no human element, for here, it seems, is a structure that was erected without a scaffold. It simply rose in its frozen majesty layer by layer. Its architecture is faultless because it is founded on pure reason, and its walls are impregnable because they were reared without blunder, error, or even hesitancy, for here human intuition had no part. In short, the structure of mathematics appears to the layman as erected not by the erring mind of man, but by the infallible Spirit of God. The history of mathematics reveals the fallacy of such a notion. It shows that the progress of mathematics has been most erratic, and that intuition has played a predominant role in it. Distant outposts were acquired before the intermediate territory had been explored, often even before the explorers were aware that there was an intermediate territory. It was the function of intuition to create new forms. It was the acknowledged right of logic to accept or reject these forms, in whose birth it had no part. But the decisions of the judge were slow in coming, and in the meantime the children had to live, so while waiting for logic to sanctify their existence, they throve and multiplied. The evolution of the complex number concept, this weirdest chapter in the history of mathematics, bears all the marks of such a development. Did the science of number wait for Weierstrass and Cantor and Dedekind to establish the real number on a logical foundation before venturing on new conquests? No, taking the legitimacy of the real number for granted, it proceeded to explore another mystic corner of this world, and emerged from this expedition the master of a new domain of unprecedented magnitude and promise. We want to trace the new concept to its source, so I resume the study of the problem in algebra which was the source of the real number. We were interrupted in this study by our long excursion into the infinite. We now return to it with a number concept vastly enriched, strongly reinforced by our new weapon, the infinite process. Instead of the rational aggregate, we have now at our disposal the arithmetic continuum. And in addition to the rational processes of finite algebra, we are now aided by the powerful machinery of analysis. Surely we should now be in a position to attack with assurance the general equation of algebra. Well, the reader who remembers his elementary algebra knows that such is not the case. The real number, too, is inadequate for the solution of all equations of algebra. And to prove this, it is not necessary to construct intricate equations of higher degree. It is sufficient to consider one of the simplest equations of its kind, the quadratic. X squared plus 1 equals 0. It defines no Dedekind partition, nor can we construct a Cantor sequence, the square of which would converge towards -1, as a limit. In the 12th century, the Brahmin Bhaskara expressed this in the simple and effective statement, quote, "The square of a positive number, as also that of a negative number, is positive, and the square root of a positive number is twofold, positive and negative. There is no square root of a negative number, for a negative number is not a square." End quote. The impulse to write x equals root -1 as a solution of this equation was curbed by the knowledge that such an expression had no concrete meaning. The Hindu mathematicians resisted this temptation, and so did the Arabs. The glory of having discovered the imaginary goes to the Italians of the Renaissance. Cardan in 1545 was the first to dare to denote the meaningless by a symbol. In discoursing on the impossibility of splitting the number 10 into two parts, the product of which was 40, he showed that the formal solution would lead to the impossible expressions 5 plus root -15 and 5 minus root -15. But, as happened in the case of the negative numbers, so here too the mere writing down of the impossible gave it a symbolic existence. It is true that it was written with the reservation that it was meaningless, sophisticated, impossible, fictitious, mystic, imaginary. Yet there is a great deal in a name, even if it be but a nickname or a term of abuse. Strangely enough, it was not the quadratic but the cubic equation which gave the impetus towards handling these mystic beings as bona fide numbers. This happened in the following way. The cubic equation x cubed plus ax plus b equals 0 has at least one real solution, and may have three. Now in the case when only one solution is real, Scipio del Foro, Tartaglia, and Cardan developed a procedure which is summed up in the so-called Cardan formula. This formula, however, breaks down when all three roots are real, for in this case the radicals entering into the formula represent imaginary numbers. Thus consider the historic equation x cubed equals 15x plus 4, treated by Bombelli in his algebra published in 1572. This equation has three real solutions, namely 4 bracket -2 plus root 3 bracket and bracket -2 minus root 3 bracket. Yet an application of the Cardan formula leads to the purely illusory result. X equals 3 root 2 plus root -121 plus 3 root 2 minus root -121. Now it occurred to Bombelli that perhaps the two radicals represent expressions of the type p plus root -q and p minus root -q, expressions which today we would call conjugate complex. If such were the case, and if the addition of such beings could be performed according to the usual rules, then the sum of two such sophisticated magnitudes may give a real number, and perhaps even one of the actual solutions of the equation, which Bombelli knew to be 4. But let me leave the word to Bombelli himself. Quote, "It was a wild thought, in the judgment of many, and I, too, was for a long time of the same opinion. The whole matter seemed to rest on sophistry rather than on truth. Yet I sought so long, until I actually proved this to be the case." End quote. Indeed, Bombelli showed that the two cubic radicals resolve into 2 plus root -1 and 2 minus root -1, the sum of which is 4. Impossibly these beings were, yes, but not altogether useless, since they could serve as the instrument for solving real problems. So Bombelli, encouraged by his success, proceeded to develop rules for operations on these complex beings. Today we have simplified Bombelli's notation by adopting the symbol I for root -1. Any complex being is of the type A plus IB. With this notation, the solution of Bombelli's equation is x equals 3 root 2 plus 11i plus 3 root 2 minus 11i equals bracket 2 plus I bracket plus bracket 2 minus I bracket equals 4. We call these Bombelli beings complex numbers, and to justify the name number we prove that they satisfy all the stipulations of the principle of permanence. Bombelli knew nothing of this principle. He was guided solely by his mathematical conscience, for which intuition is another name. Yet apart from the notation, the gifted Italian had all the rules practically in the form in which they are taught today. The first stipulation is satisfied because the complex A plus IB comprises the reals as a subdomain (B equals 0). The criterion of rank consists in stipulating that A plus IB and C plus ID are equal if A equals C and B equals D, unequal otherwise. As to the criterion of greater or of less, they are not so straightforward. However, the difficulties encountered are not serious enough to deserve special mention. The sum of two complex numbers is a complex number which is obtained by separately adding the real and the imaginary parts. Similarly for the difference. The product of two or more complex numbers is obtained by multiplying these individual numbers according to the ordinary rules of algebra and replacing everywhere the powers of I according to the schema I equals root -1, I squared equals -1, I cubed equals -I to the exponent 4 equals 1, I to the exponent 5 equals I to the exponent 6 equals -1, I to the exponent 7 equals -I to the exponent 8 equals 1, I to the exponent 9 equals I to the exponent 10 equals -1, I to the exponent 11 equals -I to the exponent 12 equals 1, etc., etc. The Bombelli operations therefore are commutative, associative, and distributive. All the stipulations of the principle are satisfied. Thus is created the complex number domain, which supersedes the real domain in the same way as the latter has superseded the rational. As a corollary, it follows that any set of rational operations performed on complex numbers leads to complex numbers. In other words, the domain of the complex is closed with respect to rational operations. Is it closed to the infinite processes of analysis as well? Or in other words, can we extend the notion of infinite sequence, of convergence and limit, to embrace the complex numbers too? An affirmative answer to this query was given in the 19th century by Gauss, Abel, Cauchy, and Weierstrass, and this fundamental fact forms the foundation of the modern theory of functions. Even in the 18th century, the complex number had already begun to lose its pure algebraic character. The famous identity discovered by Demoivre showed the role the complex number played in trigonometry, while Euler amplified Demoivre's formula by bringing in the transcendental e. Although this is somewhat beyond my scope, I must, for the sake of completeness, mention this striking identity of Euler. E to the exponent I pi plus 1 equals 0, which was considered by some of his metaphysically inclined contemporaries as of mystic significance. Indeed, it contains the most important symbols of modern mathematics, and was regarded as a sort of mystic union, in which arithmetic was represented by 0 and 1, algebra by the symbol I, geometry by pi, and analysis by the transcendental e. It is natural to inquire whether the instrument created by the adjunction of the complex numbers is adequate for the solution of the fundamental problem of algebra, determining a root of the most general equation. Already Bombelli knew that by means of complex numbers the quadratic and cubic equation can be completely solved. In other words, that the most general equation of the second and third degree must possess at least one root, which may be a real or a complex number. This followed from the fact that these equations lead to formal solutions in terms of quadratic and cubic surds. To be sure, the latter may involve complex numbers, but such radicals may themselves be resolved into the form A plus IB. Since the Ferrari method establishes a similar procedure for the equations of the fourth degree, these too have solutions which can be expressed as complex numbers, the case of a real solution being a particular instance. These facts were known in the 17th century. It was also known that imaginary roots of an algebraic equation with real coefficients must come in pairs, i.e., that if A plus IB was a solution of such an equation, the conjugate A minus IB was also one. From this it followed that an equation of odd degree must possess at least one real root. Now in 1631, the Englishman Thomas Harriot came out with the ingenious idea of putting any equation into the form of a polynomial equal to 0, a far-reaching thought, for it led Harriot to the theorem, which today we call the factor theorem, that if a be a root of an algebraic equation, then x minus a is a factor in the corresponding polynomial. This fundamental fact reduced the solution of any equation to a problem in factoring, and showed conclusively that if it could be proved that any equation has a root, real or complex, it would be ipso facto established that the equation has as many roots as its degree indicates, with the reservation, of course, that every root be counted as many times as the corresponding factor enters in the polynomial. It was surmised by Girard early in the 17th century that what was true for equations of the first 4 degrees was generally true, and in the middle of the 18th century D'Alembert formulated it in the statement that any algebraic equation must possess at least one solution, real or complex. He, however, was unable to prove this assertion rigorously, and in spite of the efforts of many who followed him, it remained a postulate for another 50 years. This assertion recalls the other statement: any equation can be solved by means of radicals. This too, we saw, was considered obvious by many mathematicians even in the days of Lagrange. Yet the comparison is unfair. Here the generalization was of the type called incomplete induction, and the falsity of the proposition only brought out in relief the danger of this method. Entirely different is the intuition which led D'Alembert's postulate. This intuition is reflected in all the proofs of this fundamental theorem of algebra that have been given since the days of D'Alembert, namely D'Alembert's, Euler's, and Lagrange's insufficient demonstrations, the proofs which Argand gave for it in 1806 and 1816. The 4 proofs by which the great Gauss established the proposition, and all subsequent improvements on these latter. Different though these proofs are in principle, they all possess one feature in common. Somewhere, somehow, sometimes openly, sometimes implicitly, the idea of continuity is introduced, an idea which is foreign to algebra, an idea which belongs to the realm of analysis. Let me explain this by a simple example. If we set capital Z equals Z squared plus 1 and Z equals X plus IY, we obtain upon substitution capital Z equals bracket X squared minus Y squared plus 1 bracket plus I bracket 2XY bracket. Now when X and Y vary in a continuous manner and assume all possible values between negative infinity and positive infinity, the expressions within the parentheses will also assume all possible values within the same range. To prove this in the general case and in full rigor is a matter of considerable difficulty. Towards this end were directed the unsuccessful efforts of D'Alembert and the genius of Gauss. But to conceive that it is so is another matter. Here is where the intuition of continuity did its work. For certain values of the variables x and y, the polynomials are positive. For others, they are negative. The variation of being continuous, there exist intermediate values of x and y, and in fact an infinity of such, which will render the first polynomial 0, and there exists another range of values for which the second polynomial will vanish. These 2 ranges will have some pairs in common. If a and b are such a pair, then a plus ib is a root of the equation z equals 0. This is what mathematical intuition suggested, and this is what D'Alembert tried to prove. Gauss succeeded where D'Alembert failed. And yet the fact that his first proof of this fundamental theorem of algebra depended on considerations of analysis rankled in his mind. So 16 years later he produced another proof. He showed that any equation of even order can by purely algebraic means be reduced to an equation of odd degree. The fundamental theorem would then be established if it could be demonstrated that an equation of an odd degree must possess at least one real root. But unfortunately this latter proposition cannot be demonstrated either without bringing in considerations foreign to pure algebra. The very fact that the proof of the fundamental theorem of algebra implies processes foreign to algebra suggests that the theorem may be of a more general scope, and such is indeed the case. The property of possessing a solution within the domain of complex numbers is not at all the monopoly of algebraic equations. Such equations as e to the exponent z plus z equals 0, for instance, and many others of a transcendental form, also admit complex solutions. The polynomials constitute only an extremely small portion of a class of functions which Weierstrass named entire. Like the polynomials, these functions will, for proper values of the variable, assume any complex value assigned in advance, and in particular the value 0. And to this class belong the most important transcendental expressions, such as the sine, the cosine, and the exponential function. From the standpoint of the theory of functions, the entire functions are an immediate extension of polynomials. Such is the basis of the theory of functions of a complex variable established by Cauchy, Weierstrass, and Riemann, a theory which was destined to become the dominant factor in the development of mathematics in the 19th century. But let me return to my narrative. In 1770 appeared Euler's algebra, in which a great number of applications of complex magnitudes was given. Yet we read there, quote, all such expressions as √1, √2, etc. are consequently impossible or imaginary numbers, since they represent roots of negative quantities, and of such numbers we may truly assert that they are neither nothing, nor greater than nothing, nor less than nothing, which necessarily constitutes them imaginary or impossible. End quote. In 1831, Gauss wrote, quote, our general arithmetic, so far surpassing in extent the geometry of the ancients, is entirely the creation of modern times. Starting originally from the notion of absolute integers, it has gradually enlarged its domain. To integers have been added fractions, to rational quantities the irrational, to positive the negative, and to the real the imaginary. This advance, however, had always been made at first with timorous and hesitating steps. The early algebraists called the negative roots of equations false roots, and this is indeed the case, when the problem to which they relate has been stated in such a form that the character of the quantity sought allows of no opposite. But just as in general arithmetic no one would hesitate to admit fractions, although there are so many countable things where a fraction has no meaning, so we ought not deny to negative numbers the rights accorded to positive, simply because innumerable things admit of no opposite. The reality of negative numbers is sufficiently justified, since in innumerable other cases they find an adequate interpretation. This has long been admitted, but the imaginary quantities, formerly and occasionally now improperly called impossible as opposed to real quantities, are still rather tolerated than full naturalized. They appear more like an empty play upon symbols, to which a thinkable substratum is unhesitatingly denied, even by those who would not depreciate the rich contribution which this play upon symbols has made to the treasure of the relations of real quantities. The author has for many years considered this highly important part of mathematics from a different point of view, where just as objective in existence can be assigned to imaginary as to negative quantities, but hitherto he has lacked the opportunity to publish his views. End quote. What has happened in the 60 years which separate the two statements to bring about such a radical change of front? Gauss answers this in his own words. An objective existence can be assigned to these imaginary beings. In other words, a concrete interpretation similar to that which identifies negative numbers with a change in sense. To understand this interpretation thoroughly, we must take a glance back into the 17th century and survey in retrospect a discipline to which I repeatedly referred in the preceding chapters, analytic geometry. When we hear about the profound changes which science has wrought in our lives, we think of physics and chemistry. We find palpable evidence of this tremendous upheaval in the mechanical inventions which have revolutionized industry and transportation. The applications of electricity have reduced the drudgery of domestic duties and developed communication between people to undreamed of extents. The achievements of chemistry have permitted us to convert heretofore useless materials into sources of subsistence, comfort, and pleasure. All this has taught man to respect and marvel at the accomplishment of these sciences. Less evident, because more diffused, are the benefits which mathematics has conferred upon us. It is true, we know, that mathematics has played its role in the theories which made these inventions possible, as well as the design of these inventions. Yet this is a matter for specialists. While in his daily life man may profit by the knowledge of the elements of which water is composed, or of the difference between short and long waves, the study of geometry or calculus will contribute little to his happiness. There are, however, among the rich achievements of mathematics some which even in this direct sense can be considered as useful inventions, because they have penetrated into the daily life of the people. To these belong our positional numeration, which made calculation accessible to the average mind. Of such immediate usefulness is also the symbolism of algebra, particularly the logistica speciosa of Vieta, which put at the disposal of the many contracted forms of general relations, heretofore comprehensible only to the few. To this category also belongs the great invention which Descartes gave the world, the analytical diagram, which gives at a glance a graphical picture of the law governing a phenomenon, or of the correlation which exists between dependent events, or of the changes which a situation undergoes in the course of time. It is a remarkable fact that the mathematical inventions which have proved to be most accessible to the masses are also those which exercised the greatest influence on the development of pure mathematics. The principle of position gave us zero, which without the concept of negative number would not have developed. It gave the possibility of standardizing equations, and made the factor theorem possible. The literal notation changed mathematics from the study of the particular to that of the general, and by symbolizing the impossible it prepared the road for the generalized number concept. Finally, the invention of Descartes not only created the important discipline of analytic geometry, but it gave Newton, Leibniz, Euler, and the Bernoullis that weapon for the lack of which Archimedes and later Fermat had to leave inarticulate their profound and far-reaching thoughts. Proles sine matra creata, children not born of a mother. In these words did the geometer Schall characterize the achievement of Descartes. With equal injustice to what preceded them, could this have been said of the principle of position and of the literal notation. The former we traced to the empty column of the counting board, and the latter we saw was but a development of a rhetorical symbolism practiced by mathematicians and near-mathematicians since time immemorial. Similarly, the great Cartesian invention had its roots in those famous problems of antiquity which originated in the days of Plato. In endeavoring to solve the problems of the trisection of an angle, of the duplication of the cube, and of the squaring of the circle, the ruler and compass having failed them, the Greek geometers sought new curves. They stumbled on the conic sections, i.e. the curves along which a general plane may cut a circular cone, the ellipse, the hyperbola, and the parabola. Their elegant properties so fascinated the Greek geometers that soon these curves began to be studied for their own sake. The great Apollonius wrote a treatise on them, in which he described and demonstrated the most important properties which these curves possess. There we find the nucleus of the method which Descartes later erected into a principle. Thus Apollonius referred the parabola to its axis and principal tangent, and showed that the semichord was the mean proportional between the latus rectum and the height of the segment. Today we express this relation by the Cartesian equation x squared equals Ly, calling the height the ordinate y and the semichord the abscissa x, the latus rectum being the coefficient of y, namely L. Significant is the fact that the Greeks named these curves and many others which they discovered loci, that is, they described these curves as the places of all points which had some measurable position with respect to some fixed reference system. Thus the ellipse was the locus of a point the sum of the distances of which from two fixed points was constant. Such a description was in fact a rhetorical equation of the curve, for it furnished the criterion which enabled one to ascertain for any given point whether it did or did not belong to the curve. And it was, indeed, in this sense that these relations were used by Omar Khayyam, who found a graphical solution for the cubic equation by means of two conic sections. Such methods were further developed by the Italian mathematicians of the Renaissance and by Vieta. In fact, it was problems of this nature that led the latter to develop his Logistica Speciosa. And last, but by no means least, consider this passage from an essay written by Fermat in 1629, but not published until 40 years later, 30 years after the appearance of Descartes' Géométrie. Quote, "Whenever two unknown magnitudes enter into a final equation, we have a locus, the extremity of one of the unknown magnitudes describing a straight line or a curve. The straight line is simple and unique. The classes of curves are indefinitely many: circle, hyperbola, parabola, ellipse, etc. It is desirable in order to aid the concept of an equation to let the two unknown magnitudes form an angle which we would assume to be a right angle." End quote. No, Cartesian geometry was anything but a motherless child. At the risk of seeming facetious, I shall say that not only had the Descartes conception a mother, the geometry of the Greeks, but it had a twin brother as well. Indeed, even a superficial study of Descartes' Géométrie and Fermat's introduction discloses that we have before us one of those twin phenomena in which the history of mathematics is so abundant. In the same century, and in fact in the same generation, we have the Desargues-Pascal discovery of projective geometry and the Pascal-Fermat discovery of the principles of a mathematical theory of chance. But these phenomena were by no means confined to the 17th century. The 18th century had the Newton-Leibniz incident, the 19th century witnessed the almost simultaneous discovery by Wessel, Argand, and Gauss of an interpretation of the complex magnitudes, the nearly simultaneous conception of non-Euclidean geometry by Lobachevsky, Bolyai, and Gauss, and later in the century the Cantor-Dedekind formulation of the continuum. Similar examples exist in other sciences. The same conception arises in the brains of two or even more men at practically the same time. In many cases the men are separated by thousands of miles, belong to entirely different nationalities, and are not even aware of each other's existence. And the differences in temperament, environment, and outlook of two such men as Descartes and Fermat are striking. How can we account for this strange phenomenon? It seems as if the accumulated experience of the race at times reaches a stage where an outlet is imperative, and it is merely a matter of chance whether it will fall to the lot of a single man, two men, or a whole throng of men to gather the rich overflow. Neither Fermat nor Descartes realized the full significance of their discovery. Both were interested in the creation of a unifying principle of geometry, Fermat from the standpoint of a pure mathematician, Descartes from that of a philosopher. Greek geometry, which found its final expression in the works of Euclid and Apollonius, did not possess such unity. Every theorem, every construction seemed more like an artistic creation than the application of general principles. What ideas lay concealed behind this or that construction? Why were certain problems constructible by straight edge only, while others required the compass as well, and still others would not yield even to the ingenuity of the Greeks, past masters of the ruler and compass? These and similar questions agitated the mathematical minds of that period, Fermat and Descartes among others. They sought the clue in algebra, so they proceeded to algebraize geometry, and analytic geometry was the result. They laid the foundation of the procedure by means of which a problem in geometry may be reduced to the prosaic manipulations of algebra. Thus the famous problems of antiquity, which began in legendary splendor and were throughout the ages a source of fascination to many mathematicians of rank, were now disposed of by Descartes in the matter-of-fact statement that any problem which leads to an equation of the first degree is capable of a geometrical solution by straight edge only. That a straight edge compass construction is equivalent to the solution of a quadratic equation, but that if a problem leads to an irreducible equation of a degree higher than the second, its geometrical solution is not possible by means of a ruler and compass only. Descartes, and the same of course applies to Fermat, was not aware that he was laying the foundations of a new mathematics. His avowed purpose was to systematize the geometry of the ancients. This, indeed, was the role which the 17th century played in the history of mathematics. It was the age of liquidation of the antique mathematical culture. I see in the work of Galileo, Fermat, Pascal, Descartes, and others the consummation of an historical process which could not reach its climax in a period of general decline. Roman indifference into the long dark ages of religious obscurantism prevented a resumption of this process for 1500 years. At the same time, by clearing away the debris of ancient mathematics, the genius of these men prepared the ground for the new. The essential characteristics of modern mathematical thought are the permanence of formal laws and the principle of correspondence. The first led to the generalized number concept. The second permitted the establishment of the kinship between seemingly remote and dissimilar concepts. Though Descartes lacked even an implicit understanding of these two fundamental principles of modern mathematics, his analytic geometry contained all that was necessary for the development of these principles. Here was an algebra which implicitly admitted irrationals on terms of equality with rational magnitudes. It was being applied to the classical problems of geometry. By direct and methodical processes, this algebra was yielding the same results that the Greeks, committed as they were to the utmost rigor, and hampered as they were by the fear of irrational numbers and infinity, obtained by ingenious but unmethodical schemes. This fact itself gave to the deductions of Descartes a tremendous pragmatic strength, for nothing succeeds like success. In the second place, analytic geometry was the first historical example of a kinship established between two branches of mathematics not only remote in nature, but known, from the very beginning of mathematics, to be in direct conflict: arithmetic and geometry. This last phase was not apparent to Fermat, Descartes, or their contemporaries, but in the course of the next 200 years it was destined to exert the greatest influence on the development of mathematical thought. I said in the preceding chapter that Descartes implicitly assumed that a complete correspondence existed between the real numbers and the points of a fixed axis. He assumed more than that, tacitly, because it seemed so natural as to go without saying. He accepted it as axiomatic that between the points of a plane and the aggregate of all the pairs of real numbers there can be established a perfect correspondence. Thus the Dedekind-Cantor axiom, extended to two dimensions, was tacitly incorporated in a discipline which was created 200 years before Dedekind or Cantor saw the day. This discipline became the proving grounds for all the achievements of the following 2 centuries: the calculus, the theory of functions, mechanics, and physics. Nowhere did this discipline, analytic geometry, strike any contradiction, and such was its power to suggest new problems and forecast the results that wherever applied it would soon become an indispensable tool of investigation. Take 2 perpendicular axes, assign a sense on each, then any point in the plane of the axes can be represented by 2 numbers. Each one of these may be positive, 0, or negative, rational or irrational. These numbers are the measures of the distances of the given point to the axes of reference, preceded by plus or minus, depending on which of the 4 quadrants determined by the axes the point may be. The principle is so simple, so natural, that it is difficult to believe that it took 3,000 years to discover it. The phenomenon is as striking as the one presented by the principle of position in numeration. The latter is implicitly contained in the structure of our number language, and yet was not discovered for 5,000 years. The former is a direct consequence of the symmetrical structure of our body, and has been used in describing the mutual position of bodies since time immemorial. It would seem indeed that it is only necessary to attach a quantitative meaning to the ideas of right and left, of back and forth, of up and down, to have a full-fledged coordinate geometry. And we find this principle utilized from the earliest days. We find it in the ancient fairy tales which describe the location of a treasure by instructing the seeker to take so many steps to the east and then so many to the north. We find that the Egyptian surveyors explicitly applied it by tracing a south-north and an east-west line and referring any object to these axes. The transition from this practical procedure to analytic geometry depended, of course, on the creation of zero and of the negative number concept. But these were known in Europe since the days of Fibonacci. Why is it, then, that the coordinate principle did not occur to mathematicians earlier? The answer may be found in the tremendous influence which Greek opinion exercised upon European thought. The emancipation of number from the inhibitions imposed on it by the Greeks was not as easy a task as it may appear to us today. Cartesian geometry assigns to every point in the plane two real numbers, and to any pair of real numbers a point in the plane. It identifies the aggregate of real couples with the points in the plane. From this it is but one step to regarding the point as a number individual, as a single number. Yet this step, too, lagged for nearly 2 centuries. In 1797, an obscure Norwegian surveyor by the name of Wessel presented before the Danish Academy of Sciences a report on the geometrical interpretation of complex quantities. This report passed unnoticed, and only 100 years later did it become known to the scientific world. In the same year, 1797, the 20-year-old Gauss was defending his doctor's thesis on the fundamental theorem of algebra, in which he implicitly used a geometrical representation of the complex domain. In 1806, Robert Argand, an obscure Parisian bookkeeper, Swiss by birth, published an essay on the geometrical interpretation of the complex. This again passed unnoticed until about 10 years later, when it was republished in a prominent mathematical journal. Finally, in 1831, Gauss, in the essay quoted before, formulated with precision the mathematical equivalence of plain Cartesian geometry with the domain of the complex number. According to this formulation, which is essentially that of Wessel and Argand, a real number represents a point on the x-axis of the Cartesian diagram. If a be such a real number, see accompanying figure, and a its representative point on the x-axis, then multiplication by I is equivalent by revolving the vector OA through a right angle counterclockwise. The number IA is therefore represented by a point A on the y-axis. If this again be multiplied by I, we obtain I squared A equals negative A, which represents the point A on the x-axis, etc., etc. 4 successive rotations through a right angle each will bring the point back to its original position. This is then the geometrical interpretation of the relations which were mentioned on page 192. Furthermore, the addition of A plus IB is interpreted as the composition of the vectors OA and OB, where A is the representative point of the real number A, and B that of the purely imaginary number IB. Consequently, A plus IB represents the extremity C of the diagonal of the rectangle built on OA and OB as sides. The complex number A plus IB is therefore identified with that point of the Cartesian diagram which has A for abscissa and B for ordinate. The addition of 2 complex numbers represented by the points P and Q respectively is identified with the composition of the 2 vectors OP and OQ, according to the rule of the parallelogram. Multiplication by a real number, say by 3, means stretching the vector OP in the ratio 3:1. Multiplying by I means a right angle rotation counterclockwise, etc., etc. The discovery of this concrete interpretation gave the phantom beings of Bombelli flesh and blood. It took the imaginary out of the complex and put an image in its place. This and the contemporaneous proof that any equation of algebra and any of a large class of transcendental equations admit solutions in the domain of complex numbers, caused a veritable revolution in mathematics. In the field of analysis, Cauchy, Weierstrass, Riemann, and others extended the whole apparatus of infinite processes to the complex domain. The theory of functions of a complex variable was thus established, with all its far-reaching consequences for analysis, geometry, and mathematical physics. In the field of geometry, Poncelet, von Stout, and others took the complex number as a point of departure to establish a general projective geometry. Lobachevsky, Bolyai, Lie, Riemann, Cayley, Klein, and many others opened up the rich field of non-Euclidean geometries. The applications of the complex number to infinitesimal geometry eventually grew into the absolute differential geometry, which is the foundation of the modern relativity theory. In the theory of numbers, Cumair invented the method of complex divisors, which he called ideal numbers, and thereby advanced the Fermat problem and related questions to an undreamed-of stage. This tremendous success encouraged generalizations. These proceeded in two directions. In the first place, the question was considered whether complex units could be used which follow other laws than I squared equals -1. A great deal of work has been done in this direction, but it is of no special relevance to this survey. In the second place, it was natural to inquire whether the points in space of 3 dimensions could also be considered as number individuals. Out of this inquiry grew a new discipline which eventually became the vector analysis of today, that plays such a fundamental role in modern mechanics. Another outgrowth of this inquiry was the theory of quaternions, founded by Hamilton, and the related Grassmann theory of extensive magnitudes. These generalizations disclosed the important fact that extensions beyond the complex number domain are possible only at the expense of the principle of permanence. The complex number domain is the last frontier of this principle. Beyond this, either the commutativity of the operations or the role which zero plays in arithmetic must be sacrificed. This forced the investigation of the properties of operations generally. The principle of permanence was then extended by dropping some of the restrictions. The result was the construction of a far-reaching theory of matrices, a theory in which a whole array of elements is regarded as a number individual. These filing cabinets are added and multiplied, and a whole calculus of matrices has been established which may be regarded as a continuation of the algebra of complex numbers. These abstract beings have lately found a remarkable interpretation in the quantum theory of the atom and in man's other scientific fields. Such in rough outline is the story of the complex magnitude. For centuries, it figured as a sort of mystic bond between reason and imagination. In the words of Leibniz, quote, "The divine spirit found a sublime outlet in that wonder of analysis, that portent of the ideal world, that amphibian between being and non-being, which we call the imaginary root of negative unity." End quote. Others regarded the complex as an empty play upon symbols which for some unaccountable reason led to actual results. They were useful, and that justified their existence, as the means justifies the end. They supplied the method and anticipated the result of many otherwise impregnable problems, so these phantoms were often invoked, but never without misgiving. And then came the day when it was shown that these phantom creatures of Bombelli were not phantoms at all, but that they had just as concrete an existence as any real number. Furthermore, these complex beings led a sort of double existence. On the one hand, they obeyed all the laws of arithmetic and were for this reason bona fide numbers. On the other hand, they found a complete incarnation in the points of the plane. They were therefore ideally adapted as an instrument for translating into the language of number the intricate geometrical interrelations between the configurations of the plane. When this was realized, the arithmetization of geometry, which was unintentionally begun by Fermat and Descartes, became an accomplished fact, And so it was that the complex number, which had its origin in a symbol for a fiction, ended by becoming an indispensable tool for the formulation of mathematical ideas, a powerful instrument for the solution of intricate problems, a means for tracing kinships between remote mathematical disciplines. Moral: fiction is a form in search of an interpretation.